So the fully implicit technique, just a reminder on what this one is. Fully implicit says, I'm going to evaluate the temperature for j plus 1, starting from Tij, but making the evaluation of the derivative at the end of the time step. So again, that requires, if you look here, where's my little pointer? So if you look here, this derivative is evaluated using the temperature vector at the end of the time step, which we don't know. That's the same as this one here. So what we need to do is go through and formulate the problem, like write out our evaluation of dt dt, and then solve explicitly for the temperatures, and then implement it in our program. So let's walk through how to do that. We'll do this just for the sake of clarity by taking the first step in time, and then we'll go through and substitute i's in, or j's and j plus 1s in where needed. So take the first step. And so let's start with what? Node 1. So I didn't show up here the derivation. I'm just going to kind of go through it using the equations we previously derived. So t at node 1 and time step 2. So t1, 2, node 1, space 1, and time step 2 is going to be equal to the temperature at node 1, time step 1, plus my evaluation of dt dt at the end of the time step. So that's going to be the quantity 2 alpha over delta x squared times temperature, now at node time 2, or node 2 and time 2. And we're subtracting from that the temperature at node 1, time 2. So previously in the Euler step, this would have been t at space node 2, time node 1, space node 1, time node 1. But because we're doing this at the end of the time step, it has to become 2 in the time index. Okay, then we add to that h bar times perimeter over AC times rho C. And then we have T infinity minus temperature space node 1, time node 2, plus 2 q dot over AC rho, AC rho times C times delta x, all of that times my time step delta t. So you would, again, I'd recommend that you do it this way. Like go through for node 1, for time step 1, and just write it out with 1s and 2s. And then every time you see a 1 in the right index, you replace that with a j, and 2s would be j plus 1. Just make sure you get which position it is correct. So this is for the first space node. I'll just kind of write it a little bit more quickly since we get the hang of it. So this is now for the ith node. 2 is equal to t I 1 plus alpha over delta x squared t I minus 1, 2 plus t I plus 1, 2 minus 2 t I 2 plus h bar perimeter over AC rho C t infinity minus ti comma 2, all of that times delta t. And this is for what? For I is equal to 2 to n minus 1. In Python, that would be I equals 1 to n minus 2. This is all the nodes I. And then the last node would be similar. It's just tn2 is equal to tn1 plus 2 alpha over delta x squared. Clear that up. 2 alpha over delta x squared times tn minus 1 time node 2 minus tn2 plus h bar perimeter over AC rho C t infinity minus tn comma 2, all of that times time step delta t. Okay, Good. So we have just, it's tedious, right? But you go through and you just make sure that you've got all the times and all the space nodes correct. And then what you would do is substitute out the j's accordingly. So let's look at how this is implemented. For the sake of time, I'm just going to show you the Python. But if you want to look, the transient fin implicit.ease file shows you how to implement this in ease. What we need to do though is, right, if we implement it in ease, we can just do it this way. Just plug it in like this. If we're going to do this in Python, we need to somehow solve for these temperatures, right? You have to include these in a way that that you can actually solve for all the temperatures because it's implicit, right? You have Tn2 here, you have Tn2 here, right? So they're appearing all across the equations. So the way to solve this is actually to develop a matrix inversion problem. So we're going to come up with a matrix of coefficients A, X, and B, and then solve that way. So I'll just flip forward here. Yeah, so this is saying what I just said. Right, we want our A matrix to be equations for node 1, equation for node 2, and so on. And then our X matrix is going to be the temperatures for the j plus 1th time step. So I kind of went through that quick, but just understand what I'm saying here. We are solving it's not a single matrix for all time. It is a single matrix for a given time step for all space. So you see that here, right? It's a given time step, j plus 1. And then we have a matrix of T1 through n that we solve to determine the temperatures at that moment in time. So one more slide, I can show you how we solve for that. So we go through, this is still the implicit technique. We take our equations that we just wrote out and we group them together. So for T space node 1, j plus 1, I have this whole mess of stuff that is multiplying that. That whole mess becomes A11 in my matrix. For T2, you get something similar. You have T2, j plus 1, A12, right? On the right-hand side, I'm going to have all the stuff that's left. Same thing goes for node I and node N. If you're looking at this, one thing that you might be confused about is I'm saying over here on the right-hand side, I have T1j appearing, I have Tij appearing, and I have Tnj appearing. How is it that I can say this temperature, which I guess we don't know, is going in my B matrix, right? B is supposed to be constant.
You already solved for it?
Exactly, right? You just hear what Doran said, we already solved for that. We're doing this matrix for j plus 1. So at j plus 1, we already know what j was. Otherwise, we wouldn't have stepped forward in time. So this is a constant as far as we care. So it goes in the B matrix. So to implement this, let's look at that finally. All right. Here's my implementation of the implicit method. So we start by allocating space for my A matrix, an n by n matrix. N is the number of space nodes. So you can see time is not involved here. So n by n. And then we have our B matrix, which is our zeros n by 1. And now I'm just going to go through, and for every place I need to add coefficients, I'm going to do that. So for the first node here, I have A00. So this is for the first space node and the 0th time step. And then first space node and the first time step. So you get these matrices that come along. So let's see what to say about this. So yeah, you're just populating it in the same way that we've talked about. And then I'm going to compute the B matrix here. One thing that I guess is a little bit unclear is the A matrix, once you compute that, that doesn't change with time. Like it might if you have certain properties that are changing with time or something like that. But my A matrix in this problem doesn't change with time. So I can just compute that once outside of my time loop leave it alone, never come back to it, and just update my B's as I need to, as I'm going through it. So here I'm doing the A matrix, here I do the B matrix, and this is the only thing that cares about time. So we go through, set the B matrix, and then I'm going to use my spsolve function to get back my temperatures and assign them to T j plus 1. Okay, so we could try to run that. Let's see, it's going to be uninteresting because if it works, it looks the same. So implicit, and it works and it looks the same. Right? Maybe the interesting thing would be, we ran this for the same number of time steps, which was 300. So what if I ran it for a value that was way below the critical time step? So 30, right? It still solves. So there might be error involved, but it's stable and it's solving. That's the benefit of the implicit method. I can maybe press my luck, right? Let's see if I can do this with 10. So you can see there's error, but it still solves. Okay. All right. Let's see what else we can get through here. All right, I'm going to flip back. Let's just look at the remaining ones. So I'm skipping this what if we reduce slide just for the sake of time. The takeaway there is, changes the time constants. It's not terribly interesting. So let's look at the Crank-Nicholson method. I don't want you to write all this out, but Crank-Nicholson again is taking two estimates of the derivative. It's an implicit technique because it takes one estimate from the end of the time step and one estimate from the beginning. So it's like a combination of implicit and Euler's. And you do that and you take the average of those two and then use that to step forward in time. So when we make this evaluation, here you have your Euler's step, which is explicit in time, right? You see this Tj here appearing. And then over here you have the j plus 1 appearing. So just the same as you would do to deal with the implicit technique, you can go through and solve this. The stuff that you know from the previous time step, the j stuff, that can go in your B matrix. And you can formulate it basically the same way. So this, you can look through the notes if you want to see this example, and we'll look back for implementation. But you end up with a really similar approach. You solve for the temperature using matrix inversion for the current time step Tj plus 1. So that should be the same. Again, can run it. Gives us the same answer, so we're happy. Last one I think we had was integral methods. What I'm going to have to do is just post the examples there, but for the integral method, you can use this thing called solve IVP. Solve IVP is an initial value problem solver. So all you have to do is give it the function f dt dt, give it a range of times, and then give it an initial temperature, right? An initial condition. You give it that, and then it'll just step forward in time. And it computes the right time step to take. So it's really, really simple to implement. You just use the same derivative function. You come up with the state equation, the function for that, and then you just let it go. OK. Any questions before we wrap up?
Are you going to animate it?
Am I going to animate it? Of course I'll animate it. Let's see. So let's do this. Yeah, and actually you can do this in your homework. So we're using Crank-Nicholson. So there you go. So there's our function. The heat flowing into the fin, and the entire fin starts kind of moving up. So this is kind of fun. You can do that. You can do it with any two-dimensional problem that you want. Ones that have a time component to them are especially interesting. So. OK. Thanks, everyone.